Good evening, everyone, and welcome to the webinar on bio-based and earthen materials. My name is Sourour, and I'm a PhD candidate at the SIAM Laboratory, University of Pau and Pays de la Dour in France. And I am very delighted to share with you the work carried out by my team and myself during my engineering internship, which focused on the influence of mechanical loading on compressed earth breaks exposed to fire. In today's presentation, I will begin by setting the research context. After that, I will move on the materials and methods. Following this, I will present the results and analysis. Finally, I will conclude. Beginning with the research context. Historically, earthen materials have been used for thousands of years and their durability is impressive. Many historic earthen buildings have survived for centuries. And today, around 8 to 10% of the world's population still lives in earthen houses. As we all know, the construction sector is a major contributor to global CO2 emissions. Earthen materials here offer a highly sustainable solution as they require little energy for production, are recyclable, locally available, and serve as an eco-friendly alternative to fired bricks and conventional concrete. Their application also is highly adaptable, as almost any clay-containing soil can be used for construction. Earthen walls provide excellent thermal regulation due to their high thermal mass and inertia. Yet, challenges remain. Their mechanical strength is lower than the cement-based materials, and the structural safety of load-bearing walls under fire is still poorly understood. Understanding this interaction between fire exposure and mechanical loading is exactly the focus of our study. Despite their advantages, earthen materials face significant knowledge gap regarding fire behavior. There are currently no established standards and studies remain scarce. In real-life conditions, walls are often subjected to loads during a fire, making it essential to analyze the performance of compressed earth breaks and their combined mechanical stress and high temperature to ensure safe, sustainable construction and guide for future building design. One of the most critical phenomena in the fire behavior of construction material is spalling, defined as the progressive or violent detachment of the material layers during fire exposure. In his research, Abdullah concluded that on compressed bricks, earth exposed to fire, thermal instabilities can arise due to their coupling of thermal, hydraulic, and mechanical effects. As illustrated in this schematic, as the temperature increases on the heated side, the water contained in the pores begins to evaporate. Part of this water migrates toward the cooler side, where it accumulates in pores, leading to buildup of internal pressure. At the same time, the loss and movement of water reduce the mechanical strength and cohesion of the material. Once the internal pressure exceeds the material's resistance, cracks develop and surface layers may detach, resulting in spalling. Here we have the spalling phenomena is shown by an AI-generated illustration. Having set the context, I will now present the material and methods used in this study. Before diving into the methodology, I would like to present the main objectives of this study. The first one is to compare the behavior of unstabilized compressed earth breaks with semi-stabilized breaks under fire conditions. The second one is to explore the effect of water content on fire performance. For this purpose, breaks were conditioned at different relative humidity levels, 0%, 75%, and 100%. Finally, we aim to investigate how mechanical loads affect the fire behavior of compressed earth breaks. Tests were conducted under three levels of applied stress: 0, 1.25, and 2.5 megapascals. The raw materials used in this study are as follows. The soil was obtained from the Nagent brickwork factory in Toulouse, France, and it was characterized using standard Proctor compaction tests, and the optimum water content and optimum dry density are summarized in this table. For stabilization, a CEM 3A 52.5L cement containing 35% clinker was supplied by Ikiom in Imeng, France. The materials produced were designed to have a compressive strength of approximately 5 megapascals, comparable to hollow-fired brakes used in buildings. Two main types of brake were investigated in this study. The first one is the unstabilized compacted earth brake, referred to as SW50, produced under a compaction pressure of 50 megapascals. The second one is the cement stabilized earth brake, referred to as SWC 3.5, compacted at Proctor energy level with 3.5% cement relative to the total weight of the soil. In this table here, we have an overview of the two brake types highlighting their apparent and dry density, also their compressive strength in megapascals. And the other table provides the legend explaining the abbreviation used, say S for soil, W for water, and C for cement. Our samples were manufactured as bricks of 20 by 10 by 5 centimeters and cured for 20 days in sealed plastic bags. Moisture equalization was then performed under controlled conditions. 0% relative humidity by oven drying at 80 degrees Celsius for 4 days, 75% relative humidity in sealed containers with a sodium chloride solution at 23 degrees Celsius, and 100% relative humidity in saturated conditions, both for 15 to 16 days. The corresponding water contents for each condition are summarized in this table. As expected, higher relative humidity leads to higher water content, and cement-stabilized bricks retain more water compared to unstabilized ones. Before the fire test, all bricks were wrapped in aluminum foil to ensure uniaxial heat and moisture transfer. To study the fire behavior of the bricks, we set up a controlled experiment using a mobile gas furnace. It is occupied with a gas burner and thermocouples, and we followed the ISO 834-1 fire curve for 30 minutes. As shown in the graph, the measured temperature closely follows the standard curve. Each test involved two bricks placed between concrete support with rock wool insulation on the sides to reproduce uniaxial heat and water transfer, similar to what happens in real wool. A uniaxial load was applied during heating to stimulate structural conditions. As demonstrated by Abdallah 2024, two tests reproduce a reproducible pattern, which is why we performed two tests per loading conditions. And here we have a video when the set test was performed. Here we can clearly see the fire from the gas burner. Having described the materials and methodology, I will now present the results of the fire tests together with the observations and analysis. Here we can see a summary of the fire tests in this table, where the results are averaged from two tests. The legend indicates the color coding. Stable samples shown in green resisted for the full 30 minutes, which represent the test duration, while unstable samples shown in red failed earlier when the brakes could no longer withstand the applied load. In addition to the duration, the table also reports the number of broken pieces larger than 10 millimeters after sieving. What clearly emerges from this result is that the 75% relative humidity condition is the most unfavorable one, as it's the only one case where instabilities occurred. By contrast, under both 0% and 100% relative humidity, the two types of brake showed consistent resistance across all loading levels. This graph here highlights how load intensity affects spawning in the brakes and shows the percentage of broken pieces. For SW50, the unstabilized brake, stability was maintained at 0 and 100% relative humidity, but under 75%, instabilities occurred at all loads, with a maximum effect at 1.25 megapascals. For SWC 3.5, the cement-stabilized brake, stability was maintained at 0 and 100% relative humidity for all loads, and also at 75% relative humidity under zero load. However, at higher loads, 1.25 and 2.5 megapascals, instabilities were observed. As shown here in this photo, at 75% relative humidity, spalling is much more severe in SW50 than in SWC 3.5. Moreover, for SW50, fragmentation is higher at 1.25 megapascals than 2.5 megapascals, which is the maximum effect. Whereas for SWC 3.5, the opposite trend occurs with more broken pieces at 2.5 megapascals. Now we will analyze the behavior of both brake types. For SW50 at 0 megapascals, the brake shows high sensitivity to water content, with instabilities occurring at 75% relative humidity. At 1.25 megapascals, thermal instabilities are again observed with a pronounced sensitivity to 75% relative humidity. Here, a maximum is identified where the closure of cracks perpendicular to the load and heated phase leads to a buildup of pore pressure. At 2.5 megapascals, sensitivity to water content remains high, but the opening of cracks parallel to the loading direction enhances permeability, releasing pore water and reducing pore pressure, which minimizes the spalling. To summarize this part, please pay attention to the animation. Here we have a brake, and generally the brakes contain like small cracks in multiple directions. When a load is applied, some cracks perpendicular to the loading close, and combined with evaporation from the fire, pore pressure builds up, detaching layers and causing spalling. Then, as the load increases, cracks parallel to the loading open, allowing water to escape and lowering pore pressure, so reducing spalling. For the cement stabilized brake, we don't have the same phenomenon. SWC 3.5 at 0 megapascals shows low sensitivity to water content. At 1.25 megapascals, thermal instabilities occur associated with the closure of cracks perpendicular to the heated phase, leading to an increase in pore pressure. At 2.5 megapascals, spalling becomes more pronounced while cracks opening parallel to the heated phase occurs. It is not sufficient to fully relieve the pore pressure, resulting in greater fragmentation under this higher load. Finally, based on these results, I will conclude with key findings and share some perspectives for future research. To conclude, our study gives a comprehensive idea of how fire affects compressed earth brakes under different moisture and load conditions. First, comparing the two brake types, we see that unstabilized earthen brakes are more sensitive and show greater thermal instability than cement-stabilized brakes, regardless of the applied load. Second, regarding water content, 75% relative humidity stands out as the most unfavorable condition for both brake types. And third, looking at the influence of mechanical loads for unstabilized brake intermediate loading at 1.25 megapascals closes cracks perpendicular to the heated phase, which amplifies thermal instability. When the load exceeds this value, cracks parallel to the heated phase open, relieving pore pressure. But for cement-stabilized brakes, thermal instabilities grows proportionally with increasing load. Overall, these findings highlight the critical interplay of water content, relative humidity, and mechanical stress on the fire behavior of compressed earth brakes. To further investigate the fire behavior of these brakes under mechanical loads, we plan to conduct additional tests. For the unstabilized compacted earth break, we will examine external load ranging from 0.5 to 1.25 megapascals to identify the onset of a pessimism effect. For the semi-stabilized break, SWC 3.5, higher applied loads will be tested to check whether a critical pessimism exists for stabilized samples. So if you are interested in further details, these articles offer a comprehensive overview for the methodology and key findings of our project. This marks the end of my presentation. Thank you for listening and I am happy to take any questions.